Okay. So, dear participants, it's a great pleasure for me to introduce our today's speaker, Denis Seletskiy. He is an associate professor of engineering physics and holder of Canada Research Chair in ultrafast and quantum photonics at Polytechnique Montreal. He received his Bachelor of Science degree in physics from the University of Alaska, Fairbanks in 2001, and a PhD degree from the Optical Sciences and Engineering program at the University of New Mexico in 2010. He continued with the National Research Council postdoctoral fellowship at Air Force Research Laboratories from 2010 till 2012, and a 5-year junior group leader position at Marie Curie Second College Laboratories Marie Curie Research Fellowship at the University of Constance, Germany. In 2017, Seletskiy established the PentaQ laboratory at Polytechnique, which is focused on advancing theory, laser technology, and metrology protocols for time domain quantum photonics. Since October 2022, he's leading a European-Canadian consortium on mid-infrared quantum technologies for sensing. The title is MIRA-QLS. And today he is giving a lecture at our seminar. Please, Professor Seletskiy, the floor is yours.
Thank you very much, Andrei, for a very kind introduction. Let me share my slides here. Okay. Okay. All right. Well, thank you. Let me adjust here. Yeah, so thank you very much for showing up for my talk. It's my great pleasure to interact, at least virtually, with all of you. As I was mentioning a bit earlier to Andrei, I really wanted to come to Ukraine to interact with Berlin students in Kharkiv and maybe go around other cities. And of course, then these horrible events happened. Russia has really opened up this war, and this is unthinkable. So at the moment, unfortunately, I cannot be with you in real space and time, but I do hope that for a swift resolution of this, for peace, for victory of Ukraine, and soon, hopefully, I could come and visit you all in person. But for now, let's do what we can. And so it's my pleasure to give this virtual seminar titled Experimental Quantum Electrodynamics. So it's a little bit provocative, I think, on purpose, because I do know that students are in attendance. I was a student once, and I kind of really like those talks that provoke thought and creativity. And this is my way of hopefully speaking to those of you who find this fascinating. Okay, so let's get going. So first, I would like to thank my collaborators at Polytechnique Montreal, my group, postdocs, students, then my former colleagues at the University of Constance, Professor Leitensdorfer, and all the students that we co-supervise together. Then I have collaborators at KAIST in South Korea, Andrei Moskalenko, and some of the work that I'll present toward the end of today is going to be given through my collaboration with a group of Maria Chekhova at the University of, at Max Planck Institute for the Science of Light. And finally, I still work in collaboration with University of New Mexico, some of the professors there, including my research advisor, Mansour Sheikh Bahai, who unfortunately passed away last year. Okay, so very briefly, so the topic of my research group is time domain quantum photonics. And, as Andrei mentioned in the introduction, in order for me to get this going, I need to do several things. So I'm experimentalist. So this is largely experimental group. So on the one hand, we need to develop sources of light, classical light and quantum light, metrology protocols, and this is kind of the input. And in the output, we really tried to apply the techniques that we're developing for sensing and quantum spectroscopy, some of the quantum electrodynamics, let's say foundational questions, at least from the experimental point of view. And then we are also doing technology development. So there's a lot of activity around all of these topics. Of course, I don't have time to get into this in about an hour that we dedicated to the presentation. By the way, if you have questions, definitely feel free to interrupt. I don't see you, so either just unmute your mics and speak up, or maybe type your question in the chat, and one of the moderators will let me know that there's a question. So please feel free to interrupt and ask questions. So anyway, in this about an hour that I have, I decided to focus mainly on these two works. So detection of vacuum field, which is kind of, I'll build up to this from the pedagogical point of view. And then toward the very end, I'll tease you with some very recent results on extreme nonlinear optics with quantum light, something that in my mind is still quite fascinating, and I think it's the new frontier in experimental quantum optics. Okay, so let me, keeping this pedagogical approach in mind, let me start by referring to this lecture given by Richard Feynman back in 1959, famously titled "There's Plenty of Room at the Bottom," where he essentially motivated the central idea that to increase the spatial, that you need to increase the spatial resolution if you want to study and manipulate matter, quantum degrees of matter on atomic length scales. And of course, since then, middle of 90s, we've seen beautiful examples here from IBM Research Lab in Zurich, for example, but many more, where people have arranged, in this case, iron atoms on a copper plane. And this is the image of individual atoms, or let's say probability of finding electrons, so wave function squared, and you can see so-called quantum coral. So you can see the iron atoms arranged in this stadium-like fashion, and you can see that there is an interference pattern forming inside of this coral, and you can see this wave of standing wave of this interference. This is corresponding to the probability of finding electrons. So this is really fantastic. And of course, this kind of intimate picture of quantum mechanics is enabled by us being able to control matter on atomic scales.
I beg your pardon.
And I would like to...
So what's on the picture in the center and around the circle?
So this is, I don't know precisely how this is done, but let me, kind of imagine. So we can take, for instance, an atomic force micro. So this is a transmission electron microscope, right? So this is a type of microscopy that plots probability density of finding of electron on a surface with an atomic resolution. Unfortunately, I don't have here the resolution. I apologize, but this is from that article. Someone can quickly Google it. So this is probably, that the atoms are separated roughly by a nanometer or so. So this is man-made arrangement of iron atoms via some technique. So the iron atoms are then placed, iron 48 is placed in this coral configuration, and then the tip is scanned.
How did they manage to place in a circle?
This I don't know from the from the top of my head, but for instance, we know how to position quantum dots. For instance, this is the work that I've done in the past. You can take an atomic force microscope, for instance, a tip, and you can push, in that case, quantum dots, so much larger than a single atom. But in principle, techniques exist, techniques are available, tip-based techniques
Okay,
that
one by
would, for
one.
instance, yeah, exactly,
Okay.
one by one.
Thank you.
It's not a self-arranged, as far as I know. All right, good, thank you. All right, so this is kind of the central idea, right? So this is spatial degree of freedom. And what I would like to pose here is that, of course, by the space-time equivalence, we can port the statement of Feynman directly to the time domain. So now we can say that if you want to increase temporal resolution, you can access and control matter on atomic timescales and actually quantum degrees of matter. So that's my personal motivation for what I would call time domain quantum photonics. And I'll give you some flavor of that as I go. So what timescales are we talking about? If I plot time on this logarithmic scale, somewhere here would be very slow, like me moving this mouse, milliseconds, seconds. This is what I call macroscopic response. And here we have subatomic world, so something that's moving extremely fast. Here we have 10 to the minus 18 attoseconds, 10 to the minus 1 zeptoseconds. So you start getting into this regime of high energy physics. And somewhere in the middle of this logarithmic scale, between 10 to the minus 15 seconds or femtoseconds and 10 to the minus 12 seconds or picoseconds, we have most of the response of condensed matter that we know and interact with, from semiconductors to superconductors to pretty much any solid state based technology that we use, that especially when we rely on optical and optoelectronic properties. These fundamental degrees of freedom of matter that control this response, their natural timescales lie between one few femtoseconds to picoseconds and longer. Here I listed some of them, right? So, electron-electron correlations, electron charge lattice correlations, thermalization, ultrafast thermalization, loss of coherence, phonons, spin relaxation mechanisms. This is more or less that range. And if I take 1 over this time scale, I get into the frequency domain. So then the frequency range of interest is very loose here, but it's between 150 terahertz and half a terahertz. So this is what I call terahertz to mid-infrared frequency range. And it's very interesting, obviously, for this reason, that if we were to develop spectroscopic tools in this frequency band, we can then study all of these degrees of freedom directly. Moreover, and this is what we're going to talk about today, we also now at the tip of, let's say, experimental realization, where we can also measure quantum fluctuations of electromagnetic fields in this frequency band. So now we have an ability potentially to look at electromagnetic fields, their fluctuations, their quantum fluctuations, and through that study quantum degrees of freedom, quantum correlations, quantum, some observables that go beyond the mean field values, which is accessible by classical spectroscopy. In principle, we can think about unlocking this new regime of time domain quantum spectroscopy. So this is my interest. I want to pose this question: can we measure fields directly, quantum fluctuations of these fields, particularly in this frequency range? So this frequency range is not only interesting because of these fundamental degrees of freedom and matter. Of course, there are also a lot of engineering applications. This is so-called fingerprint regions sometimes, and complex molecules have very distinct absorption spectra, absorption characteristics in this spectral band. So if we have an instrument that can discern all of these features, we can, with very high precision, identify complex molecular structures, and through that we can think about discovery of new drugs, pharmaceutical research. We can think about monitoring, pollution, for instance, environmental trace gases. We can think about medical diagnostics, something that's pertinent to Canada, where I'm from. We have, in the winter, for instance, a lot of fog. And if we think about self-driving cars, which rely on LiDAR technology, laser and detection ranging, then we need LiDAR technology that is able to see through fog. So it turns out that in the mid-infrared spectral band, there are some regions of the spectrum where light can penetrate between the absorption states of water molecule and hence, see through fog. So these kind of, let's say, engineering and technology motivations of doing research in this frequency band. And just because I'm here and I want to also kind of interact with you and maybe inspire some of the potential collaborative efforts that we can develop, I want to mention that at the moment I, through being a professor at Polytechnique Montreal, run a consortium between Canadian and European partners, and our project, as Andrei mentioned in the introduction, called Miracles, which stands for Mid-Infrared Quantum Technology for Sensing. It's collaboration between Toronto and Montreal, Polytechnique Montreal on the Canadian side, and on the European side we have two universities in United Kingdom, Poland, University of Warsaw in Poland, University of Paderborn in Germany, EPFL and ETH Zurich in Switzerland, University Milano Bicocca in Italy, and Universidad Autónoma de Madrid in Spain. And all of our effort, this consortium, is essentially a concerted effort between theory and experiments and technology to really try to create next generation quantum technologies specifically for sensing. And we also have some industry partners here from Germany and from Switzerland. And these are some of the participants in the consortium. You might know some of them. Feel free to contact either myself or whoever you know from this list and ask for potential collaborations. We would love to talk to you and explore common interests together. Okay, but let me get now to the fundamental part of my talk. So, as I said, for me, what's interesting is measuring quantum fields in the time domain. So I have to start by telling you, how do we measure in the time domain? What are our techniques? Well, it turns out that we always use an oscillator, right? The oscillator is the best way to measure time or frequency. These are commensurate quantities. So how do you do this? Well, for instance, we can envision having a wristwatch. So now we have a wristwatch. The clock is ticking. And some of the best wristwatch has an experimental uncertainty of plus minus a second per day. So now we have an uncertainty delta t. We have a time scale of the measurement, day, capital T, and what we call fractional uncertainty, which is fractional accuracy, which is the ratio of these two quantities, is an order of 10 to the minus 5. Okay, so 10 parts per million stability of such an oscillator, which is not bad if you don't want to be late for your meeting, but of course that's not good enough for some of the physical measurements. So another kind of an oscillator that we can think about is a laser itself. So if we think of a single mode laser, it emits electromagnetic waves, and if I plot electric component of that electromagnetic wave, it would oscillate like a pendulum up and down, right, in time. And if I take a Fourier transform, it would be a very narrow distribution at a particular frequency. Well, the frequency is an optical frequency. So for instance, if I were to give this lecture in person, I would be using a green laser pointer with a frequency corresponding to around 700 terahertz. And the width of that oscillator is on order of 5 kilohertz. Well, it can be different values. This is something that I'm giving from this narrow line with laser company that's in Quebec, in my home province in Canada. So anyway, if we compute fractional stability of this source, we have to take 5 kilohertz over 10 to the 15 hertz. We get 10 to the minus 12 fractional stability. So this means that the light is oscillating. Yes.
Which kind of, this is a maser, or which kind of laser?
This is This is
Optical.
Maser. M stands for microwave. This is laser. L stands for light. So this is indeed a light wave. So this particular laser emits at a wavelength of 1,500 nanometers, which corresponds to 200 terahertz. But if I was using a green laser pointer, the optical
neon
laser, yes.
Neon laser.
For instance, yeah, helium neon laser is one example of this, but yeah, there are many other lasers. You're right. Yeah, so light carries enormous frequency, right, of the oscillation.
Just wonder that 5 kilohertz is just very good.
Right, so 5 kilohertz is the width of that distribution. Yeah, so you're absolutely right. Traditional laser out of a box, like a laser pointer, would not have a 5 kilohertz line width. This is something you have to work on. So this is why I'm kind of advertising that company Teraxion, which specializes, among other things, on making narrow line width lasers. So something you can buy off the shelf for relatively cheap is 5 kilohertz line width. And that's exactly my point. So the fractional stability, which is very narrow compared to the carrier frequency, and hence the fractional stability of 10 to the minus 12. So if you imagine this optical field oscillating in real space, or in real, say real space, it means that it's making an oscillation every femtosecond or so, and it propagates in space by over that one cycle of light. It propagates in space maybe by only few microns, right? Wavelength of light. So let's say 700 nanometers. And now that this line width, this coherence length rather, of 20 kilometers implies that the light doesn't skip a beat. It just oscillates precisely as a pendulum, up and down in sinusoidal motion, from here all the way down the street, 20 kilometers. And somewhere there it starts what we call decohere. The phase starts jumping once in a while, such that the Fourier transform starts broadening. So it just gives you an example of some of the precision we can obtain with optical technology. So precise measurements most often imply that you have to do them with optics. And the reason why you go from 10 to the minus 5 stability, like with a clock, to 10 to the minus 12, is because laser is a quantum, is a device that governs which macroscopic characteristics are governed by quantum transition. So the quantum phase transition, which we go from spontaneous emission of a laser below threshold, and all of a sudden, once we exceed a certain pumping condition of a laser, this spontaneous emission, all of a sudden, via, of course, stimulated emission, acquires this coherent character. And this is formally a quantum phase transition. And the quantum phase transition protects the stability of an oscillator such that you get this gigantic improvement in the stability. Well, it turns out that so far we discussed so-called single mode laser. It turns out that there's another type of technology where we call it mode locked laser. So here, instead of having a single color that oscillates in a laser cavity, we can prepare the laser to emit multiple colors, so multiple longitudinal modes. And moreover, we can introduce nonlinear optical element inside of the cavity, the job of that element will be to ensure that all the modes are emitting in phase. And if you think of essentially coherent superposition of many lasers all in phase, and if you were to take a Fourier transform of that, you would end up with the following picture. You would have a very short burst of light, as short as, as short as 1 over the number of modes that you've locked in the frequency domain. So you have a very short pulse. Then it's followed by nothingness, and then another short pulse. So we have a pulse train. And this, and depending on the number of modes you lock, so easily in the lab we can lock up to 1 million modes. And 1 million modes implies essentially a 10 femtosecond pulse. So this can be very short pulse, and another short pulse, and another short pulse. So you can see how we transposed this very high stability of an oscillator to a very high stability of a pulse train. And it turns out some of the recent work at National Institute of Standards and Technology in Colorado, United States, have shown that such lasers, okay, you have to do additional preparations that I'm not discussing here, but the fractional stability of such lasers can be 10 to the minus 21. This is really astronomical. So instead of this, laser not skipping a beat in 20 kilometers, like we mentioned before, now the laser doesn't skip a beat from Earth to Alpha Centauri, to a different galaxy. So this just shows you really astronomical precision. And the reason that you get it.
I can ask,
yes.
what could be the duty cycle or the period of silence between the pulses?
Yeah, this is an excellent question. So what determines separation of pulses in time is essentially the length of the cavity, right? Because what this means is you have a pulse that starts in one end of the cavity, propagates, and then exits. So it's a round trip. The time it takes for light to travel through one
so it's
round trip
based
of the
on
cavity.
the lowest frequency mode, yes?
Exactly. So depending on technologies that we have available, sometimes that time can be 100 picoseconds, sometimes it's 20 nanoseconds, sometimes it's 1 microsecond. So depending on how long that cavity is, that dictates how often the pulses come. And the number of modes that we use to lock in a frequency domain determines via Fourier transform argument how short the pulse is. Yes, so this is in essence femtosecond laser technology. So my question is, yes.
Could you comment how this lock-in is realized, so of the phases?
Okay. Yeah, so right. So this is kind of an interesting mechanism. It's essentially in nonlinear optics, and there's several ways to think about this. So let me give you maybe the simplest way to think about it, and then I'll say why it doesn't work for femtosecond pulses, and you have to think a bit further. But the simplest way to think about it is, imagine we have a cavity, and as the previous question that we had, the separation between the teeth, the modes of the cavity, is 1 over the round trip time of the cavity. So for the sake of example, let's take this case that round trip time is 10 nanoseconds, okay? Which 1 over 10 nanoseconds means 100 megahertz. So 100 megahertz is a characteristic frequency of such a cavity. So now let's imagine we introduce a modulator inside of the cavity. And we start, for instance, an electro-optic modulator. And let's start, so it's a type of device that introduces a phase shift as light propagates through this device when the voltage is applied to that device. So the phase shift is proportional to applied voltage. So now let's apply voltage that oscillates at 100 megahertz frequency, which is, remember, it's exactly the proper frequency of our cavity. Then what happens is, instead of 1 laser mode that we had originally, if you can solve this transfer function of such a time modulated response, and what you will see is you will create sidebands, and these sidebands will be exactly detuned by the frequency of the modulation, but we chose it to be exactly the proper frequency of cavity. So that what that means is we take the power of fundamental mode that oscillates in the cavity, and via the modulation technique, we transfer some of that power into the sidebands, which are also now can oscillate in the cavity. The transfer mechanism is coherent. That means that whatever phase was in the main mode, that same phase or some deterministic relationship of that phase now transfers to the sideband. So we transferred coherence from a single mode to pairs, and if we drive it hard, we can propagate that broadening to several pairs, and now pairs of modes. And now having several pairs of modes in frequency domain, in time domain, means that our energy is now clumped in these pulses. Now, this would work for nanosecond pulses, maybe a few hundred picosecond pulses. It turns out that this won't work for a femtosecond pulse. So while this is a nice pedagogical way to see how such mode locking can propagate phase coherence to sidebands via this active modulation, the best way to ensure that you have millions of modes locked is a passive modulation. And passive modulation is a nonlinear element, which essentially has some kind of an optical property which depends on the intensity of incoming light. So for instance, if we had a so-called saturable absorber, so if a single mode light is incident on it, which is very slow, the envelope of a single mode is time invariant, temporal envelope, yeah. So transmission of such a saturable absorber will be given by some value. But now let's imagine that we had some kind of fluctuation in the cavity. And this fluctuation spontaneously gave rise to some local in time, local clumping of energy. The way the saturable absorber would work is that when you have more intensity coming in, let's say, its loss function will drop. If the loss function of such a nonlinear element will drop, the threshold for lasing will also drop. So now you see that there's a nonlinear feedback in the cavity that ensures that fluctuations with highest amplitude in field will provide the lowest threshold for lasing. And this nonlinearity, coupled with the feedback mechanism of the cavity in this phase transition way, would lead after many round trips, kind of for that the phase transition, that the phase would crystallize, if you want, into this mode locked state as opposed to a single mode state. I hope that answers your question.
Thank you.
Okay. All right. So, we went from relatively poor stability of an oscillator to an extraordinary stability of the oscillator. And we can ask the question, what is the limit of that stability? We can just keep improving the technology. And so, of course, the limit of that stability is imposed by quantum mechanics itself. So, remember, our job is we're measuring fields. So far we have been measuring field, how it oscillates in the time domain. Then we were taking a Fourier transform and computing what the width of that Fourier transform is divided by the carrier frequency. That's what gave us our fractional stability or accuracy of our measurement. So we need to measure fields. That's clear. So now, if we do classical electrodynamics, we have field that oscillates in time. Remember in your first courses in physics, you can represent that temporal oscillation essentially for convenience in the complex plane. So it's a fixed radius vector given by the amplitude of the field in the time domain, and it oscillates in the complex plane at the angular velocity corresponding to the light frequency. Okay, so this is the picture that we develop. In classical electrodynamics, it's convenience. But in quantum electrodynamics, we have to understand that we can't draw the amplitude of the field precisely. That violates Heisenberg uncertainty principle. So we have to ensure that when we draw the field, we have some uncertainty band associated with the amplitude. So in the polar representation, that means that the r hat direction of our polar vectors now has some uncertainty region, but also the phase of our light wave is uncertain. How do you think of the phase? Well, roughly it's the time interval between two zero crossing events, for instance. Okay, so we have one zero crossing event here, another one here. The time difference is uncertain by, given by this uncertainty in defining the zero crossing value. So this in a polar representation is uncertainty in theta hat of our complex vector. And if you work it out with quantum mechanics, this uncertainty region is going to be given by what? Well, this oscillator picture maps exactly on the charged non-relativistic charged particle of mass m trapped in harmonic potential. And if we compute the eigenstates of that particle, we will arrive to the following energy structure. Well, it turns out that this Hamiltonian describing electromagnetic wave maps exactly onto the Hamiltonian that we use to solve these eigenstates of it, of the quantum harmonic oscillator. And so these states are also then can be applied to our thinking of electric field amplitude, or correspondingly to the vector potential. It doesn't matter. What I'm trying to say is, at the ground state, at the lowest energy allowed by quantum mechanics, it's not going to be a zero like a classical oscillator. It'll be at finite energy, and that state will have a certain uncertainty, will have certain width. Well, that width you can compute by the following expression. Is given by the frequency of that oscillator, and then normalized by epsilon naught, permittivity of free space, and then V. What is V? V is the mode volume of our cavity. So we have taken our cavity, we computed the mode volume given by the separation between the mirrors of the cavity, given by the diffraction property of the fundamental optical mode inside of that cavity. Well, they will have a volume that is used as this normalizing quantity here. Well, that E naught determines essentially, or A naught, you can, depending on which picture you're using, it determines the width of that ground state. So for the rest of the talk, let me refer to that width as essentially amplitude of vacuum fluctuations. Why vacuum? Well, this is the lowest state of excitation of electromagnetic field. The number of particles in this state is 0. And nonetheless, there's a finite energy. So this is usually called a vacuum state. And the width of that excitation, let me refer to as vacuum fluctuations. So now, in our complex representation, we essentially see that this kind of nice coherent oscillator is nothing more than a vacuum state, this uncertainty here, displaced from the origin by the amplitude E naught, all right? Okay, there are many manifestations of vacuum fluctuations. I know I'm running a little bit maybe short on time, so just maybe I'll skip most of these. They're self-explanatory: spontaneous emission, Lamb shift, Casimir effect. Maybe well, those of you who are interested in high energy physics and cosmology, this is a very fantastic realization of vacuum fluctuations. It's a theoretical proposal by Vyacheslav Mukhanov and Gennady Chibitsev. Essentially, it's a work that comes off from proposals of Andrei Sakharov, and the idea goes as follows. I'm not a high energy physicist, I'm not a cosmologist, but my understanding that the idea goes as follows. At the moment of Big Bang, if you want to ensure that we have a unified theory based on quantum fields, we have to assume that at the moment of Big Bang, or delta after the Big Bang, we have extremely small volume, space-time volume of our physics, of our universe. And you see vacuum fluctuations of our quantum fields describing everything, all the physics, are normalized by 1 over the volume. So very small volume means that the energy of the vacuum fluctuations is enormous. But remember, the universe is rapidly expanding in these early times. And as it's rapidly expanding, this normalization volume obviously grows. And that means that the vacuum contribution starts decreasing as time goes on. So this theory proposes that as you start with very extreme vacuum fluctuations at very early time, upon rapid expansion of the universe, these fluctuations freeze out and essentially become the macroscopic energy density of the universe we see today. So all these clumps of energy we see, galaxies, planets, stars, this is a result of a particular configuration of vacuum fluctuations that happened after the Big Bang. And this is, I think, a beautiful demonstration how something microscopic, such as vacuum fluctuations, has actually a cosmological consequence, at least in theory. Anyway, so this is vacuum fluctuations. And what I would like to propose is to kind of as a thought experiment, let's climb this ladder. All right, so remember, my motivation is to be able to sample quantum fields in time, right? So here I'm plotting the amplitude of a quantum field. Here I say phase, but remember, phase in my complex representation is just omega, the angular frequency of light, times t, time. So you can think of this x-axis as time, essentially. So if we were to think about vacuum state, we know that the expectation value of the vacuum state is 0, of the amplitude of the vacuum state, but it has some fluctuations. This is exactly that vacuum fluctuations we discussed in the previous slide. So this is understood. Now, if we go to the next rank of our quantization, to this next state, so-called Fock state 1, or so-called single photon state, we have the following picture. We have probability of finding a photon in this Fock state 1, or rather amplitude, to measure amplitude, let me be very precise. Probability to measure amplitude of electromagnetic wave corresponding to an energy content of 1 photon, essentially in 2 bands, with 0 probability of measuring a field in the origin, and these 2 bands at some kind of plus and minus 1 normalized amplitude. This already shows you peculiarity of quantum light, right? So there's no carrier wave to think about here.
Sorry, what does mean amplitude minus 1? Amplitude is a positive value.
Amplitude minus 1. It's normalized by some. It's a dimensionless amplitude. Let's say it's normalized by proper dimension coefficient with carrying some dimensionality, just so it makes the illustration easier. That coefficient, that it's essentially all that stuff in front that we discussed in the previous slide. It includes epsilon naught, frequency, mode, volume, all of that. If you were to, okay, so that means that at a particular point in time, what I have to say is classically, I have to measure the expectation value of the field to be 0, right? It's kind of a very interesting thing. It's really a quantum state of light. And if we keep climbing more, Fock state 2, then we get even more interesting structures. Of course, students say, well, there's no time dependence. This is boring. Why is no time dependence? Well, all of these are eigenstates of a Hamiltonian. By definition, they're time stationary. But of course, as we know from quantum mechanics, now we can take a superposition of these eigenstates and we can construct any time dynamics. So Glauber in the 60s already has done this for classical radiation, for instance, coming out of a laser. So you have this, oscillatory structure, as we discussed before, and this is so-called coherent state, usually depicted as this alpha. And it's nothing more as a particular combination of a vacuum, single Fock state, so 1, 2, 3 Fock states with proper weighting coefficients. And Glauber showed if you take that particular superposition, you get out your classical state. And now the uncertainty is indeed that vacuum state displaced by the classical amplitude corresponding to that coherent state. Okay, so far so good. I want to ask now a question. How do we measure the time evolution of this field? At the end, this is my program. I want to measure how these fields evolve in time. Okay, so the standard way to measure field in quantum optics is so-called homodyne detection, and it works as follows. Suppose this is the state that we want to measure. It's a state of unknown light coming in. We have to know something. We have to know the frequency of that state. If we know the optical frequency of that state, we're doing optical homodyne detection. So we need to know the frequency of that state. Knowledge of that frequency helps us to build so-called local oscillator. It's another laser which is at exactly the same frequency as this unknown field that we want to study, and it's a very large amplitude, this coherent state we just saw from Glauber previous slide. Now, what we do formally is we multiply the two, which is nothing more than we do the interference, and we look at two orthogonal projections of that interference. We look at the in-phase interference, which would be essentially projection in our complex representation on the, let's say, real axis. And then we look at the quadrature so 90-degree phase of that interference term, and we look at the projection on the y quadrature. So now particular quantum state here casts essentially shadows on real part and imaginary part. And if we let that state evolve and we keep measuring how these shadows, how these projections change in time, this is essentially tomography. So now we collect all of this projection information, and from projections we can reconstruct via tomographic transform, we can reconstruct the original distribution. This is essentially a Wigner function of the state, right? And how do you perform multiplication? Is it
what could be the intermediate frequency? What is the order of it? It's not optical already. It's a radio frequency.
So this is optical. This is optical.
Local,
so we take
local oscillator. It's frequency tuned or no? Or fixed?
So okay. So we can get into this. Let me address this on the next slide. But to answer the question, of course, but to answer the question right off the bat, so of course, if the detuning of these two, we don't have to keep the local oscillator exactly at the same frequency of as this input state. We can allow for certain detuning. Certain detuning in frequency, 1 over that detuning implies a time scale, and essentially that time scale has to be matched to the response time of the photodiode. So if the photodiode that's measuring this signal is very fast, that it can tolerate certain detunings. But still, just to give you a sense of scales, these fields oscillate on a femtosecond time scale. The best detectors we have a response time of tens of picoseconds. So you see it's 10,000, so 4 orders of magnitude difference in the response time. So let me, for the sake of example, focus on the optical field, but keeping in mind that, yes, you can play some games on the detuning by increasing the speed of the photodiode. Okay. All right. So how do you do this multiplication? Well, multiplication is nothing more than an interference term, right? So when you look at the interference, let's say Michel's interferometer, you take one field plus another field, the whole quantity squared. You have intensity of one field, intensity of the other field, and then you have this cross product. This cross product is the multiplication. All right, so those of you who know quantum optics, were maybe enjoying this or not, now even those who know quantum optics have to pay attention, because here I'm already saying something new. Okay, for students, it's of course a nice, hopefully pedagogical review. So quantum optics, quantum mechanics is all about detection, is all about the detector. So in the context of homodyne detection, what is our detector? The answer is the local oscillator. Let me demonstrate it in the following way. Let's imagine that what we have as an input of that state we want to analyze is the state which contains many frequencies. And let me represent that frequency content of that state as some kind of a distribution function, okay? Now, when we do this multiplication, as we discussed in the previous slide, we have to essentially, well, it was multiplication, so signal given by a multiplication of two fields, the local oscillator and the quantum field. And it's clear that if the local oscillator was at a different frequency, then the signal on the slow photodiode will be 0. The only way we can ensure that we have a finite signal on the slow photodiode that's registering this interference is when the local oscillator frequency, optical frequency, is roughly commensurate with the frequency content of the unknown field. Moreover, because of this multiplication, the signal will only come where the two functions are overlapped. So now you see kind of the meaning of a local oscillator. So we have an unknown quantum state of arbitrary superposition of frequencies, and the selection of a particular shape of the local oscillator at a particular carrier frequency omega naught projects certain information out of that unknown quantum state by the virtue of the selection of the local oscillator. So local oscillator is a detector. It selected particular modes of the quantum field. Now, if you want to reconstruct the entire quantum field, you can either scan the frequency of the local oscillator or perhaps use a different function of a local oscillator that's more broad. These are the details. The main point to understand is what's doing the detection in homodyne detection is a local oscillator, and this shape is determining the signal. Now, listen. So we have linear interaction, right, which is given by this multiplicative term. So another way of saying this is we have a detection event which is localized in the frequency domain. We have chosen particular frequency omega naught, and around that omega naught, we obtain information of this quantum field. Well-defined frequency. Remember our discussion at early slides. We had field that was oscillating like an oscillator in time, up, down, up, down. We were taking Fourier transform, and the more extended was that field in the time domain, remember 20 kilometers distance to Alpha Centauri, the narrower was the representation in the frequency domain. So hence, localization in the frequency domain, narrow in the frequency domain, implies that the information we're getting about this quantum state is distributed along some time interval. That's much longer than the oscillation cycle of that field, right? So what I would say, this is a traditional language or traditional realm of quantum optics. We have well-localized frequency, hence we have so-called photon picture. We don't have any information on the sub-cycle nature of that quantum field. We are doing cycle averaged detection. And this is kind of a very nice and very fruitful regime of quantum optics. So now let's take that picture. And now let's do an analog, but in the time domain. Okay, so now the quantum field under study is distributed in the time domain. It's actually a field that oscillates in time. Now, what I want, by the same argument here, I wanted local information of that field at some frequency omega naught. Here I want local information on the field, but around time tau naught. So what I need to do in order to carve out this interval of time out of the total wave function of the quantum field is I need a product, right? I need a product, and that product is given by the amplitude of the local oscillator at time tau naught and the amplitude of the quantum field at the time tau naught. Okay, so somewhere here. Notice several things. One, the local oscillator here shown in green is much narrower, or say it's narrower than the oscillation cycle of the quantum field. So by doing this multiplication, being local in time domain, we're picking up particular amplitude of that field, and it's with sub-cycle information. However, the penalty we pay is because we are localized in time. By the virtue of Fourier transform, we are delocalized in frequency. And hence, we don't know, in principle, we're agnostic to the energy content of that field under study. We don't know it from a single measurement in time. And my supposition is how we had information localized in frequency, and it gave us a photon picture and a regime of quantum optics. Here we have undefined frequency. And this is really a question of local fields as opposed to photons. And this is really the language of quantum electrodynamics and not quantum optics. Sometimes, some people get scared of quantum electrodynamics. So, okay, you can also call it subcycle quantum optics. My point is, this is kind of a regime which is complementary to the frequency domain. Here we have local information in frequency. Here we have local information in time. One thing to note, you see, what we required is a product of two fields in the time domain. Product of two fields in the time domain means that if you take Fourier transform of each of those fields, product in time means cross convolution and frequency. What it means that we generate new frequencies in the frequency domain. So this necessarily entails a nonlinear optical response. So here it was enough to just take a Michelson interferometer, put a beam splitter, interfere the two modes on the beam splitter, there was no nonlinear response at all. And here we require nonlinear optical response. We need, similarly to how that we were putting nonlinear optical element inside of the laser cavity, we need some kind of a nonlinear element which optical properties, for instance, reflection, transmission, depend on amplitudes of these fields. Unlike in this case where it's just amplitude agnostic elements only. Okay, I hope that's clear. So, this is I put it mainly to tease some of the students that are maybe theorists rather than experimentalists, just to say that, okay, I'm really painting this time domain picture as access to quantum electrodynamics. So you see, we're taking fields and we're getting information out of fields, not in reciprocal space, not in frequency, not in wave vector, but really in space and in time. And if you kind of follow some of this discussion in quantum electrodynamics, or later known as quantum field theory, for instance, by Peskin here, or better yet, if you were to read a Nobel Prize lecture by Feynman called The Development of Space-Time View of Quantum Electrodynamics, you know, I encourage you to read it. It's a fantastic read. So read. I'll read this out loud. To summarize, this is after a long discussion of how Feynman looked at solutions of electrodynamics from the Hamiltonian point of view. Hamiltonian, remind you, is energy conservation, which means you're in a reciprocal space. For photons, energy is the frequency, so you have to be localized in frequency to respect energy conservation and so forth. So he went through this Hamiltonian description of electrodynamics, Lagrangian description of quantum electrodynamics, and then he writes, to summarize, when I was done with this as a physicist, I gained two things. One, I knew many different ways of formulating classical electrodynamics, as I just mentioned, with many different mathematical forms. I got to know how to express the subject every which way. Second, I had a point of view, the overall space-time point of view, and disrespect for the Hamiltonian method of describing physics. I'm not so bold as to say I have a disrespect for Hamiltonian method of describing physics, but I want to motivate you is that if you want to do study of quantum properties of fields, you better do it in the so-called space-time view as opposed to reciprocal space. And this quote from Feynman underscores this point. Okay, so I come back to my point. So we have this quantum field that we want to analyze in time. We have this local oscillator, which is so short that it's shorter than half a cycle of this quantum field. I'm experimentalist. I'm saying we need those short pulses. I won't have slides to show you, but maybe in Q&A or somehow, or you have to trust me that yes, we have technologies that can access lasers with pulses as short as 6 femtoseconds. So in principle, you can imagine fields for which 6 femtoseconds would be shorter than half cycle. Which frequencies of those fields? Well, they are these terahertz mid-infrared frequencies. Remember, at the beginning of the talk, I motivated this terahertz mid-infrared band. Well, now I'm saying to you, we have a technique of actually measuring fluctuations of quantum fields in that frequency band. Okay, and then we need nonlinear mixing process. So, by the way, I don't have any questions coming, so I want to ensure that we're still connected.
No questions. Thanks.
Okay, no questions. All right. So please, if you have any questions, if something is unclear, please interrupt me at any time. So I want to discuss now nonlinear mixing process. So this nonlinear mixing process is essentially called electro-optic interaction. Okay, and the way it works is as following. By the way, I just checked, I'm at 1 hour mark, so maybe I should accelerate, but we already had some questions. Okay, so electro-optic sampling, the way it works is you have a nonlinear, a crystal, which has a nonlinear optical response. And the way this nonlinear optical response is manifested in the following way. Let's suppose that we apply a field oscillating in a slow way, this quantum field under study. polarized along certain direction. And at the same time, we apply a short probe, which we call local oscillator, that's polarized in an orthogonal direction. Then, depending on this symmetry of this crystal, we can imagine the following procedure. When the terahertz field is incident on that crystal, what it does is change the nonlinear coupling of terahertz with the nonlinear tensor of the crystal changes the polarization state of the probe. This is the formally how it changes. So it induces birefringence, change in refractive index along these different axes. And this is the amplitude of this change. It has some coefficients, and the key point here is proportional, linearly proportional to the amplitude of this applied field. So the way it works experimentally is the following. I have a polarization of the probe. After the interaction, the polarization of the probe remains the same. After the quarter wave plate, it becomes circularly polarized. Then I project back into horizontal vertical basis, and I read out the photon number difference of these two projections, and I get 0. Now, if I have at the same time as the probe field is present, in the same temporal interval, we have also overlap with the, let's say, positive and a negative, in this case, positive amplitude of the terahertz field, then the polarization state of the probe changes after the interaction. And then this change in polarization state, after you propagate through this ellipsometry, so-called, we get a positive signal. If we now change the direction of that field, the perturbing field, then polarization of the probe changes, but now ellipsometric signal is with the opposite sign. So now you see what happened. By probing polarization state of this short pulse, we can infer the amplitude of this incoming field via this nonlinear coupling. So let me show you how it works in experiments. So this is what we just described. Here I'm showing you electro-optic signal, and this is classical field. So far, no quantum yet. So this is classical field. So this displacement. And you can see that this field that we want to study oscillates like this. Notice the time scale here, 20 femtoseconds. So it's a very fast oscillation. But I can take this raw signal and I can tell you exactly via these scaling coefficients we saw in our previous slide. I can tell you exactly how that field transforms into natural units, kilovolt per centimeter or volt per meter. Yeah, and then I can take a Fourier transform of this. So notice this is essentially a oscilloscope for light. So now I have a technique, nonlinear optical technique, that measures with subcycle information how the optical field oscillates in time. I can take a Fourier transform of that, and you can see that the frequency content of that field goes from 60 terahertz or 5 micron all the way to 110 terahertz or 2.8 micron. So this is what we call terahertz to mid-infrared field. And the question I want to ask now, I'm getting to this main part, is how do I measure quantum fluctuations? Can I measure those quantum fluctuations? Now, let's suppose that I don't even have this classical amplitude. I block it off. I completely do not care about generating this classical field. I still should be able to measure something. Classically, since I block classical amplitude, I should measure 0. But quantum mechanically, as we mentioned already, we don't have 0. We have fluctuations around that 0 given by the vacuum field. So now my job as an experimentalist to compute what is the value of these fluctuations that I expect in my experiment. Okay, so I have the recipe for how to compute this. I have to know the frequency of my terahertz field, and I have to know the volume. But remember, the volume was given by a cavity. It was a mode volume inside of the cavity. But now we change the problem. Instead of being in the frequency domain, meaning delocalized in time, such that the mode fills the entire cavity, now we have a very short pulse. So the volume is not necessarily the mode volume. We can think of it as sum over all longitudinal modes in the cavity, and we would obtain something like this. But already Heisenberg, as the quantum electrodynamics is being explored, but before Tomonaga, Schwinger, Feynman work, kind of finalizing work on QED, already Heisenberg proposed that this expression is not satisfying because it treats frequency, or 1/time, on a different footing than this volume, which is in three-dimensional space. He said, well, we really need to treat this in space-time. And he said, a better way to think about this expression is essentially just fundamental constants, and the normalizing volume is a 4-volume, not a 3-volume. And this is now relativistically satisfying because there is no preferential treatment of space and time. It's treated on the same footing. And now this is kind of a very nice formula. It again underscores the fact that quantum mechanics is all about the detection. What is this 4-volume? It's the volume of the detector. So if we had a macroscopic detector, very big, then 1/very big is small. That means that the effects of quantum mechanics on very large detectors is essentially negligible unless you paid real care, right? And we have some examples of that. But in general, the quantum character of signal obtained with very large detectors is virtually suppressed to 0. This is correspondence principle. And contrary, if you have very small detector, 1/small is huge. So you amplify the quantum effects by selecting the detector to be very small. So now, what is our detector? Our detector is the local oscillator in the time domain, which was the probe pulse. How do we make it small? Well, we already prepared it in a 6 femtosecond duration. So that's as small as we can make currently experiment. But we can also focus it in space. So by focusing it as small as we can in space, by generating very short pulse, we can calculate based essentially on this formula and converting it to experimental parameters that we obtain some field value of 20 volt per centimeter corresponding to vacuum fluctuations as detected by our focused femtosecond pulse. If this was the entire story, it probably would have been detected a long time ago. What we need to understand is, in addition to this vacuum contribution to the measurement, we also have shot noise contribution. Even if we didn't have coupling to the vacuum modes provided by this electro-optic crystal, and if we were simply to just put a photodetector and look at the probe, the fact that the number of photons in the probe is not infinite but finite, they obey Poissonian statistics. That means that the number of photons per pulse event fluctuates as a square root of n, where n is the number of photons. So these fluctuations, what I would call trivial or shot noise fluctuations, we have to take them into account in our measurement. And if we work out the effective field for these measurements, we get to 65 volt per centimeter. Now, in our measurement, the quantum field that's coming in this case vacuum, is completely uncorrelated with the shot noise at the optical frequencies. So we have to add them in quadrature, and we obtain that the excess noise, I'm sorry, I'm missing one, should be 1.04%, so 104%. So we exceed shot noise by only a few percent, and that's the idea that I want to say. So if we were to do this measurement, we would have to measure noise, and we have to measure noise that's larger than shot noise by 4.7%. As experimentalists, it's hard to measure noise, and moreover, hard to measure changes in noise. We have to implement some kind of a procedure by which we can turn off this coupling. Say, okay, without the coupling, we only have shot noise. With the coupling, we have shot noise plus coupling to the vacuum field, so this extra 5%. How do we turn off shot noise? How do we turn it, or rather, how do we turn, not shot noise, I misspoke. How do we turn off coupling to the incoming vacuum? Well, remember, the vacuum is scaling 1/the volume. So all we have to do of the detector, all we have to do is we have to increase the volume of the detector, keeping the number of photons in the probe fixed. This will suppress coupling to the vacuum field, but it will preserve the number of the shot noise in the probe, and hence this would be our way to measure this differential noise. So we have to vary the space-time volume of our probe pulse. So now I'll accelerate because I've kind of hopefully pedagogically set up how do we do this. So now
I'm sorry,
experiment.
may I ask a short question on previous slides?
Of course. Yes.
Is it enough with this small amplitude of the vacuum noise for the nonlinear crystal to work for mixing? You show on the previous slide that it's like 1/2 a kilovolt per centimeter. Will it will have these nonlinear properties at these amplitudes?
Yes. So, well, turns out that they will, and the way to think about it is here's the effective amplitude of just Poissonian fluctuations of the field inside of the probe. Okay, so we have some fluctuations of that, and what we are saying is this nonlinear signal, exactly as you pick up. So the signal is provided by the nonlinear coupling between probe and the vacuum. That's 1/3 of the shot noise in terms of amplitude, right? So this is calculation based on coefficients of the nonlinear coupling and everything. So this is what calculation has shown. It's sufficient. Now, if we were, but see, it's the reason it's so high is because we didn't only take the very short pulse, we also focused it very hard. So if we were to defocus our probe, then the amplitude will drop from 20 volt per centimeter perhaps to 0.1 volt per centimeter, and then it will be unmeasurable. So is it measurable? Well, let me answer like this. So what we do is we take, the only way we can modulate the vacuum is, like I said, by dilating the space-time volume of our probe. So here I'm showing you a histogram of 10 to the 8 electro-optic readouts. So essentially we have an experiment with a very short pulse coming in, and we record every event of that electro-optic readout gives us. So we get one voltage, another voltage, and we convert them to be amplitude of electro-optic signal here, and the probability of that signal gives us the shape of that distribution. Now we do two things. We obtain this with a short pulse, and then by this prescription we just discussed, when we have to dilate our space-time volume, we dilate the temporal extent of our probe to 100 femtoseconds, keeping the number of photons in the probe fixed. We have ways to do it. If you put essentially a transparent piece of glass which has strong dispersion, femtosecond pulse broadens, but there is no absorption. So there is no there's no loss of photons. The number of photons remains the same, but temporal structure of the pulse changes. The envelope of the pulse changes. So if we do that, we obtain a different distribution. And you can see that shown here in black. So you can see it, because the number of photons is the same, the integral of these two distributions has to be the same. And you can see that the black distribution is higher around 0, which is the expectation value of our class. If we were to do classical signal measurement, we should obtain 0, right? So the distributions are centered at 0. And with the long pulse, the distribution is higher in the origin. That means it has to be narrower in the wings. So the black distribution is narrower than the short one. So that means with a short pulse, we obtain slightly more fluctuations. If we were to deconvolve these two distributions, we obtain that the measured value of this additional noise on top of shot noise is 18 volt per centimeter. And from theory, we get 20 volt per centimeter. So this was published a few years back. We also worked out with Andrei Moskalenko, we worked out a theory for this, and it was self-consistent. Now, so remember, it's all about dilating the space-time volume. So instead of dilating the temporal extent of the pulse, now we can keep it at 6 femtoseconds, but we can dilate it in the spatial extent. So we go from condition where electro-optic crystal is in focus to slightly out of focus. And here I'm plotting only the vacuum contribution obtained from the deconvolution procedure as we shown in a previous slide as a function of probe spot radius. So you see, when the probe is large, the vacuum field is 1 volt per centimeter. It's close to being unmeasurable. The error bar is huge. But as we make the probe smaller and smaller, the vacuum contribution grows. This is log scale. And if we plot it on a linear scale, we can see this hyperbolic dependence. The red line here, it's exactly this expression. No fitting parameters whatsoever. So here's the bandwidth of our pulses. Here's the spot size of our pulses, refractive index, fundamental constants. No fitting parameters. We do the measurement. We plug those values. We obtain this characteristic scaling, and we plot this. So it seems to also confirm the experiment in these two orthogonal ways to dilute the probe, dilate the probe, I should say, both in time and in space. And what I want to say is, we have done these experiments when I was in a group of Professor Alfred Leitersdorfer at the University of Constance before I joined Polytechnique. We were for a while the only group in the world that was able to do this. And then a few years after that, another group at ETH Zurich in Switzerland have performed the same experiment, experiment different in two ways. One, they have taken this electro-optic crystal completely in the bath at 4 Kelvin. I'll tell you why in a second. And another thing they have done, instead of, in our experiment, we have one probe and we're plotting the fluctuations of that probe. Here they have two probe fields that they can either delay in arrival on the crystal in time, or they can separate them in space. And what they measure is a correlation, first order correlation, so G1 measurement between these two probe fields. So they look at field correlations. Here's the correlator that they study. SEO is electro-optic signal, and as I said, they can vary the arrival time on the crystal or the displacement between the two fields in the crystal. And here they show experimental dependence of this G1 function as a function of frequency. And then here's, and they're able to fit it. The reason why they need to cool down to 4 Kelvin is they operate, remember, we operated around between 50 and 100 terahertz, so mid-infrared. They operated essentially around 3 terahertz. If you think about if you think about experiment that's measuring noise, you have to say, well, in addition to the quantum field that you want to analyze, you have to, if you set up a scene noise, you have to believe it that it should also see black body radiation noise, right? So electromagnetic radiation associated with black body, the environment of the laboratory at 300 Kelvin, it emits uncorrelated photons, thermal photons, and those photons should then couple to your experiment and produce additional noise. The amplitude of that noise at low frequencies is quite high. That's why they had to cool the entire detector to low temperature. At 50 to 100 terahertz, it's such high frequency that black body radiation is there but negligible compared to this low frequency. And hence, we didn't need to cool down our experiment as I showed from 2015. Anyway, this is a small detail, but just to show you that using the same principle of space-time volume of the probe, this group of Jerome Feist at ETH Zurich was able to show that, yes, you couple to the vacuum modes in different frequency regime and different temperature, but they cooled it down to 4 Kelvin, and at this temperature, they have shown that their experiment is dominated by quantum noise. And moreover, something that they have done very recently is they have done an experiment where they show that depending on how they separate these two beams, they actually can separate them to be at such distances where the effective communication time will be faster than the speed of light. So for the two measurement points to communicate, that information has to flow faster than the speed of light, so-called non-causal contributions. And they have shown that in this correlation measurements that they do, they have non-causal contributions. So this goes a little bit into quantum electrodynamics. I don't want to get into these for the time being, just to show you that this is not the only group in the world that has done this. This is a second confirmation. So I know that I'm okay. Maybe I'll ask Andriy, how much more time do I have?
I think 10 minutes is okay.
10 minutes? Okay. All right. Good. Thank you. So I'm sorry for this, but we had some questions, so that slowed me down a little bit. So let me just very quickly recap what we did. We have taken nonlinear crystal. We have taken a local probe, which we called local oscillator. It's a classical light coherent state, contains on average 10 to the 8 photons. And what we did is, by analyzing electro-optic coupling between this vacuum modes that are coming in and this local probe, we're able to measure a little bit of extra noise on the probe, polarization fluctuations of the probe, and we ascribe them to the vacuum field that's incoming on this nonlinear crystal with the probe. And I don't want to get in those details, but if you have questions, I'm happy to do it either now or offline. But this is an ideal scenario for measuring Gaussian states of light. So for instance, vacuum is one example of this squeezed vacuum, displaced squeezed states. These are all examples of so-called quantum states of light, which are described by Gaussian statistics. Okay. Now, what we have realized that if you don't want to measure Gaussian state, but you want to think of maybe more exotic states, you're bounded by the fact that you have classical probe. Classical probe is another state of Gaussian statistics, and it just doesn't couple well to these non-Gaussian quantum states of light. So what we've proposed fairly recently is a new technique where we take this electro-optic readout, as I presented it, and we do it with quantum states of light. For this, we need the following. We need quantum states of light which are 10 femtoseconds in duration and contain 10 to the 8 photons on average. And you say, my God, what is this? How can you do this? So let's discuss very briefly in the last few minutes that I have. So the way to obtain such fields is by a technique called parametric down conversion. It's a nonlinear optical technique. The way it works is the following. You have a pump, let's say a femtosecond pulse. It comes into this nonlinear crystal, and it produces 2 photons. This is Chi2 interaction, so it's a 3-wave mixing. It produces 2 photons, so-called signal photon and an idler photon. And these 2 photons have to satisfy momentum conservation. So the wave vector of the pump has to be the same, has to have the same length as the projection of the emitted photons in the direction of the pump. So in this case, signal and idler photons would add up to be the same as in K pump. And that would naturally dictate the angles at which the signal and idler would emit. And then the energy conservation tells you that the sum of the signal frequency and idler frequency has to be the same as the pump. And this is energy conservation. It dictates which frequencies those signal and idler photons are emitted. And you can show that if you cascade this process, meaning that at the very beginning of the crystal, you have this pair production. By the way, these 2 photons is a standard way to produce entangled photons. So these photons are entangled or correlated in all degrees of freedom, in the time of arrival, in frequency, in polarization, in the number of photons. So this is probabilistic, but nonetheless an excellent source of generating quantum states of light. So now if we now take this pair production and we cascade it, so we put more and more and more of these crystals together, essentially take a thicker crystal, what you can show is the amplitude of these fields will grow exponentially. So this is so-called parametric amplifier. And in this case, formal way to show this is a parametric amplifier of vacuum fluctuations. You have coherent field. Here you have input vacuum modes. And what happens at the output, the coherent field propagates, and the macroscopic number of photons in the signal and idler comes about from the amplification of the vacuum field that was incoming into this crystal. Okay, so the technique that we proposed is to say, okay, if we have such a crystal, we have all the possible modes incoming of the vacuum, at the input of this crystal. And if we prepare conditions just right, what we can make is output of this crystal will produce 2 pulses of light, very short as the pump light, and they'll be correlated. So if we now send one of them on electro-optic detection, exactly as we discussed in the first part of the talk, and we do some kind of a post-selection protocol on the other pulse, then we can have this conditional measurement. And we have shown that if you do some type of conditioning, for instance, keeping only high photon counts of the pulse, then in the Wigner representation, that corresponds to negativity. And that means you by virtue of post-selection on one of the branches, you prepare a non-classical state of light in a lower branch. And this non-classical state of light then is a resource for electro-optic sampling. We have shown this in 2021 paper. All right, that's good. But now what we need to do is we need to essentially prepare these pulses in a single temporal mode. One way to think about it, it's nothing more than how do you think about the number of temporal modes? Well, it's given to first order by the duration of the pump here, pump light, and it's normalized by the coherence time of this nonlinear crystal. Coherence time is nothing more than 1 over the phase matching time, okay? So if you play around with this momentum matching condition as we discussed, and you do it such a way that 1 over that momentum matching condition gives you 10 femtoseconds, the same as the duration of the pump pulse, 10 femtoseconds, then the number of modes is guaranteed to be 1. So we have done this experimentally. Here we generated signal pulses, idler pulses. Notice the number of photons per pulse is approaching 10 to the 8. We looked at the joint probability density. Anyway, long story short, we generated this in a single spatiotemporal mode, well, with some admixture, 6% of the next mode. We have 10 to the 8 photons per pulse. They're extremely broad. In the frequency domain, you can see it spans from 1,000 nanometers to 1,600 nanometers. So it's enormous bandwidth. And we have taken a nonlinear optical measurement where we analyze the temporal structure of these pulses, and we obtain that their duration is 3.6 cycles of light. So this is, I think, one of the first demonstrations of quantum light, which has macroscopic occupation, 10 to the 8 photons, and it's ultra short. Its duration is only 10 femtoseconds or so. And literally, I have 2 minutes, so let me finish with this. 10 to the 8 photons, this is great. This is already accessing nonlinear regime of light-matter interaction. But a little bit about field resolve detection of quantum fields, kind of tell you a little bit about macroscopic, experimental quantum electrodynamics, that picture between frequency and time domain, and very briefly in the end, how we can actually use very bright states of quantum light to drive some interesting regimes in nonlinear optics. Thank you very much.
Yeah, thank you, Denis, for a wonderful talk and for all the effort that you put to make it really understandable. And I understand that you are very limited in time, but it's great. Thank you.
Thank you so much.
We have questions. Yeah. So
yes,
Mykola, please.
Thank you very much. I confess I didn't understand everything, but I will look into the references that you gave. Well, at the beginning of your talk, you mentioned that your aim is to measure quantum fluctuations of the fields which are close to coherent fields like that. And I expected that you will show pictures like in the textbooks on quantum optics, where people measured the quantum scatter around the sinusoidal curve of a laser field. So, but I didn't notice any picture like that in your talk. So can you comment, do you do things like that, or this is not interesting anymore?
Mm-hmm. So thank you for this question. So first of all, indeed, those curves that you mentioned, those scatter plots, as you call them, let me kind of go to the very beginning. That's more or less what I was motivating. So yeah, that coherent state from Glauber, for instance, as I was drawing, right? So it says displacement, classical displacement, and the scatter plot there, the scatter width of that scatter was essentially given by the Wigner distribution of the vacuum mode, which is otherwise sitting at the 0. So what we say, okay, for us to measure the vacuum mode, we can get rid of the classical amplitude, right? We know that that this coherent state is nothing more than a displaced vacuum by classical amplitude. So we don't need to put the classical amplitude. We can show only the vacuum. So something we have not done, but indeed, if you were to keep a very small classical amplitude, we could have shown that at every delay point, you have that histogram that I showed, and then at every delay point, it's a superposed histogram on top of a classical field that we measured, and you would reconstruct that that oscillation. Now, this is kind of a, let's say, trivial point, but I should have emphasized it. But let me give more credit to your question, because the point is the following. We used classical light to do this measurement. We used coherent state. And that was my point that I maybe glossed very briefly. Because it's coherent state, it actually couples very well to the variance of the incoming quantum light. So indeed, the vacuum mode. So, this coherent state is a good state to analyze. Vacuum, squeezed vacuum, displaced squeezed states, exactly as I say. But we have also shown theoretically that if you have a more non-trivial state at the input, for instance, a Fock state, a cat state, some other non-Gaussian states, that probe being classical does not couple very well to higher order statistical moments. Remember, when we were plotting the Fock distribution, it was no longer a scatter around 0. It's a scatter of 2 bands at some. We even had someone ask a question, what is +1, what is -1 in that amplitude? So the amplitude was never 0, even in the scatter representation. It was either a band of positive, not either, and positive, a band of positive amplitudes and negative amplitudes at the same time. So if we had a state like this, that statistical distribution or scatter, as you call it, that's no longer Gaussian. It has, mathematically speaking, it has high order statistical moments. And to probe those statistical moments, we have shown it's not enough to have classical probe as at the top of the slide. We need to go to quantum light. So I'm sorry that I went very fast, but this is what I was trying to show, that by using parametric down conversion, we can create such quantum light. And that quantum light we have shown theoretically in this PRL that's depicted, that's shown here on the slide. We have set up a proposal which shows that high order statistical moments of those non-Gaussian states of light can be measured more efficiently with these quantum probes. And so just to maybe wrap up my question, you wanted to see an oscillating field with some scatter. What I'm saying to you is we are working right now in the lab exactly on this. We know how to prepare states of terahertz light that resemble Fock distributions, very non-trivial scatters, and we will superpose them. We are doing this experimentally. We superpose them with a classical displacement amplitude, and we are measuring such states that hopefully, I can maybe in several months or maybe we meet in a conference next year, I can show you those plots that we measure experimentally.
Okay, thank you.
Thank you. I'm sorry, I don't see, Are there more questions? Oh, I don't hear you, Andrei. I think you're muted.
Oh, sorry. I have question on the last slides where you have 10 to the 13, I think, photons, right?
Okay.
What is
Okay.
duration there? Maybe I missed pulse duration.
Yeah, so no, it's a great question. I didn't say. It's 25 femtoseconds. We measured it, but I didn't show it on the slide. So it's 25 femtoseconds pulses. The center frequency is around 200 terahertz, wavelength of 1.6 micron. And yeah, and the amplitudes are now atomic, volt per angstrom.
Looks very impressive.
Yeah, thank you.
So I have another question, but I don't know whether it's to official part or unofficial. So about the shorter pulses than 6 femtoseconds. So you mentioned that you
all of that is published, so no problem.
Okay.
Yeah.
So you what is the shortest then?
Okay.
You can reach.
So the shortest pulse, so this is a great question. So shortest pulse is a pulse which contains a single cycle of light. Because you can show fundamentally that the electric field of a pulse integrated in time has to be 0. Otherwise, the pulse will carry infinite energy in the far field. So the field has to integrate to 0. The only way this can be if the field is single cycle. So you cannot have half a cycle fields. In the far field, it's only single cycle. So once you set up a frequency, let's say 200 terahertz, then the single cycle condition implies that the bandwidth of that pulse has also to be 200 terahertz. And that would imply that 1/200 terahertz is 5 femtoseconds. So we have shown that at 200 terahertz carrier frequency, we can approach 4.6 femtosecond pulses, which is electromagnetically the shortest in the far field, the shortest. Now, what is our procedure to us as an community? What is our procedure to generate short pulses? We have to move the carrier frequency to higher frequencies. Hence, this whole push of attosecond science. By going to UV, extreme UV, now the center frequency is much higher. And then in principle, if we can support bandwidth as high as the carrier frequency, then we can approach very short pulses. So the record, as I know of, still is in Spain at ICFO, and it's 42 attoseconds. So this is the shortest pulse we can produce as photonic community. And it's only because the carrier frequency of that is no longer 200 terahertz, but it's actually, I forgot, 1.3 petahertz or even higher. Yeah.
Thank you. So I do not see other questions. So if it's not the case, let's thank the speaker again. So for questions, for answers, and all the participants as well. Thank you very much.
Thanks, Denis, for the
Thank you
nice
so
talk.
much. Thank you very much, Andrei, Sergey, and everyone who attended, who asked questions. Thank you very much.
Yeah, and hope to see you then in person in Ukraine.
I hope so too, for many more reasons than just physics, but yes. Okay. All right. Thank you very much. Ciao. Bye-bye.
Bye-bye.
Thank you.
Bye.
Bye.
Thank
Bye.
you. Bye-bye.
Sayonara.